Okay, this is our presentation on flexible diffusion models of long videos. Um, so to get started, the problem and motivation for this paper is generating long, coherent videos that are still photorealistic, they have temporal coherence, and they're still able to be ran on hardware today. And so this is just a result of what this paper was able to make. So we can see here that this 25-minute long video, starting off with this input red frames, which are basically pre-existing frames that the user gave as input, is still able to generate frames at 25 minutes later that are still photorealistic and coherent. And so the main contributions for this paper, the first one being making a diffusion-based video generation architecture, creating their own video driving data set called Carla, which has some interesting statistics that you can calculate with it. And then finally, the most important one is this novel training objective, which allows for flexible sampling on any frames during training, along with still being applicable for resource constraint settings. So the way this model works is it uses basically frame-to-frame generation. So to relate back to what we've seen in the past with our sort of standard diffusion model, is we have some input conditioning, which we usually see text, and then it generates an image. But in this case, we use images, which are denoted as the Y set of input conditioning frames. And this is typically going to be seen as highlighted in red throughout the rest of the presentation. And it's going to generate these blue X set of output sample frames that are conditioned on these input frames. And so to look a bit closer to the architecture of the model, so we have this series of frames that represent our video, and we can see here we have these input conditioning frames here that are already pre-generated, they're already known, and the order that it's selected on is all dependent on the sampling schemes, which we'll get into later. And you have some output frames that you want to be sampled on that are currently noise right now. And so you collect these frames together and you pass them into this video unit, which is basically similar to the standard unit we've seen with this additional K dimension. And this K dimension basically represents the upper bound of the amount of input conditioning frames and the output sampling frames that you can pass into the model. And so it's going to use these frames to generate the new noise frames, and it's going to denoise them and create these new frames based on those previous frames. And so now I'm going to pass it over to Niall to get a bit more into the architecture. I'm sorry, into the methodology.
Right. So as Shane has mentioned, in general, the way to generate long form videos requires this idea of small sequential steps where you condition on some set of frames to generate the next set of frames. Now, the key thing to note here is that there's multiple ways you can choose what frames you want to use for conditioning. Do you use frames at the start? Do you use frames, near the middle? Do you pick them contiguously? Are they kind of spaced out? So a lot of these different samples can occur, and it may affect your result. So when we're talking about sampling schemes, it does have a pretty strong impact on the results that you get. So the idea or the question in this paper is, can we generalize a model to train on any sampling scheme? So before I kind of expound on that, we'll kind of give some more detail about what I mean by sampling schemes exactly. So building off the example Shane was giving before, this is probably the most intuitive or straightforward method of video generation, which they call autoregressive, where essentially you have some set of conditioned frames. So these red frames exist, and you use these frames as a conditioning prompt to your diffusion model to generate the next 3 frames here. And so at each diffusion step, you kind of keep going on along the process and generating your video using these conditioned and generated frames. And you'll even notice that the frames that the model itself generated are used for conditioning in the future. But obviously, this isn't the only sampling scheme you can use to generate videos. Maybe you want a larger temporal receptive field, or basically you want like more temporal information when sampling. So this could be another sampling scheme that you use, where you can see the condition frames are a little more spread out in this case. They kind of span a longer timestamp. And you generate frames in this manner and then infill in between to kind of, again, get a larger temporal receptive field. So these are two sampling schemes that are known and have been used in previous papers and other generative methods. And in this paper, they also provide some other types of sampling schemes, which they denote long range and hierarchy too. We'll discuss these later, but the idea is that there's multiple ways you can choose conditioning frames and sampling frames to generate a video. So to mathematically, like formally define this, what's happening is we have these two sets, x sub s and y sub s. So x sub s is essentially a set that contains the indices for the frames you want to sample. So all the blue frames are in this set right here. Now, these frames are generated based on the conditioning frames. So that's what is contained in the set y sub s. So we have some frames we condition on to generate these future frames at an s number of diffusion time steps.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
So the method that they propose in this paper, they call flexible sampling, and by proxy, they call the whole process flexible diffusion. And the idea is, can we arbitrarily generate or sample? They're used interchangeably. Can we arbitrarily sample frames using an arbitrary choice of conditioning frames as well? So the reason this is important is there's an important distinction to make first as well, is that everything we'll be talking about from here on out, flexible sampling and arbitrary choice, this is all during training time. We'll talk about what happens at test time a little bit later, but just keep the training method in mind here. So what's important to note is that the optimal sampling scheme at test time for certain data sets is dataset dependent. So the sampling scheme you use at test time for one data set may not yield the best results for another data set. So during training, you want some model that is robust to any sampling scheme. It's been trained on basically every sampling scheme you can think of. So at test time, you can change what sampling scheme you'd like to use to generate the best results. Now, at test time, these optimal and adaptive methods that you can use are discussed in the paper. We'll lightly touch on them, but if you want some more details, you can look at the paper for that. Now, before I kind of go over what is the sampling scheme they use in the training process and what is flexible sampling, there are some design considerations that will kind of help build intuition on this. So at training time, like I mentioned, we want to have some sampling scheme that randomly chooses frames to sample and randomly chooses frames to condition on as well. And I say random, there is some logic in there, but I just use random for simplicity. But there are some considerations we want in this sampling scheme. We want this sampling scheme to show our model multiple timescales or spacing between frames. So sometimes we want our model to be conditioned on a completely continuous block of conditioning frames and sample a continuous block of frames, kind of like what we saw in autoregressive. But we can also space these frames out as well, and that can, again, increase temporal coherence. So the sampling scheme should randomly change the spacing between the frames. We also want to take into account multiple groups of disparate frames. So maybe throughout the video, you want to condition on multiple groups of frames that aren't touching, and you also want to sample or generate frames of multiple groups that aren't touching. So our sampling scheme should also generate these types of samples. You may want to generate different numbers of frames. So if you're generating a video where there's a lot happening, there's multiple objects and multiple motions happening in the video, you may only want to sample a small number of frames at a time, maybe 1 or 2 or 3 frames, because there's a lot of information to capture. But if you're generating a long video where maybe there's long spaces of time where there's nothing really going on or there's not a lot of objects, you can probably generate 10 or 15 or more number of frames in those diffusion steps because there's less information to capture. Now we're talking about flexible sampling. We're talking about keeping this arbitrary. So there are very, very few rules that the authors put into their sampling scheme. But I'll just go over just a couple. There's only 2 of them. One of them being here, where all frames need to be sampled once, which is pretty straightforward. Every frame in the video should be generated. We don't want to leave out any frames or any gaps in the video. And more importantly, we don't want to condition, a frame should never be conditioned on before being sampled, before being generated, which is also pretty straightforward. You can't use a frame to condition on if it simply doesn't exist. So the high level idea is that there's a bunch of design considerations that'll give us the best sampling scheme. And we want to encode all these considerations in some distribution that we can pick from. So we denote this as the distribution U, which depends on X and Y. So we want to sample from this distribution. Every single time we sample an example from this distribution, it'll give us some frames that we should sample at that diffusion step. And it'll also give us the frames that we should be conditioning on as well. Now, as Shane had mentioned before, there's a threshold that we put on these two values, which is K. So the intuition behind this is if we didn't implement K and we said we let the model sample however many frames it wants to generate and however many frames it wants to condition on, it could theoretically choose 150 or 200 or 300 frames to sample in a single step. And that's just way too many frames to generate in a single step, and it won't be able to capture all the information in a specific video. So K can be limited to 10 or 20, which basically means in a single diffusion step, the combination of the number of frames you're sampling and the number of frames that you're generating shouldn't be over this number, so 10 or 15. So it kind of motivates some smaller steps of diffusion, and you'll see an example of this later. So first, we'll get into this methodology now of how this flexible sampling actually works and what this distribution is. But we'll start with a visual example here, which can kind of help describe the process. So here, what we have is we have two variables here. We have n is equal to 30 and k is equal to 10. So what that means is each row is a length of 30 frames. So these videos are 30 frames long. And k is equal to 10 means that you can count all the squares in each row will be less than or equal to 10. So the number of frames you're sampling, or even the number of frames you're sampling and the number of frames you're conditioning on, will be no more than 10. So again, this kind of limits what the model can do in a single step. The last thing to note is that these rows don't correlate to each other. So this isn't sequentially going down this graph. So this first row is not correlated with the second row, and the second row isn't correlated with the third row, and so on and so forth. What this diagram is supposed to show is you have some distribution U that I mentioned before that kind of drives our sampling scheme. So if I were to pick just a bunch of random samples from this distribution, what would it look like? And that's what this graph shows you. So if I picked one random sample from this distribution, I could get this first row where we kind of see some evenly spaced sample frames that have no conditioning on it. If I chose another sample, maybe I would get something like this, where it's much more spaced out and the frames kind of span over the entire video. The first frame is here, the last frame is here. We can see some more close together examples where maybe it's only sampling these two groups of frames together. We can also see there's conditioning examples as well, where we're generating these frames conditioned on a frame before and a frame after, and so on and so forth. So how are we actually building this distribution we're choosing from, and what is like the nitty-gritty details behind that? So I'm going to go over this algorithm too, which is kind of the core of this sampling algorithm. And what this is basically doing is saying at training time, we want to sample, again, I'm going to sound like a broken record, the frames that we're generating and the frames that we want to condition on. So all of this information is encoded in this distribution U. All we need to do is feed in this n and k value. So that's kind of the example here. If we have n equal to 30 and k is equal to 10, here are some examples. So we have our two sets. We have the set of frames we want to generate at a single step and the frames that we want to condition on a single step. And we move on to identify some variables. So n group is in one specific step, how many frames are we going to generate? So that's why it's limited by k. So in this case, if we're generating one frame, and let's say k is equal to 10, we know we're going to condition on about 9 frames because the number of conditioning frames, the number of sampling frames should be the same. If you sample 2 frames, conditioning would be 8 frames. If you sample on 3, so on and so forth, all the way up to if you want to sample k frames in a single step, then there should be no conditioning frames in that. The second variable that we're going to define is the spacing between each frame. So here you kind of see there's some equal spacing with a little bit of variance. Here there's very little spacing, just one frame dividing these two groups. There's also a lot of spacing in this example here where it's kind of spaced out across the entire video. So this variable, given you sample from this distribution and you get some variable for how spaced out each frame should be. X group denotes the first frame in this set. So in this case, this index would be the third index. This would be the 0th index. So obviously, if you have a low index, the sampling is starting at the start of the video. But you can see, like in this example here, the sampling is starting in the middle of the video. So that's denoted by this variable here. And lastly, there's an observed variable, or what you can think of as an indicator variable, which basically says, have I seen this example before? Have I randomly generated this specific row of sampling frames, or have I not seen it before? And that'll come into play a little bit later. So what happens is we generate all of these variables, and it'll result in one of these rows, any one of these number of rows. Obviously not limited to this, but these are some examples. And we can think of this as a single group. So this one row is a group of frames that we're going to sample on. This one row right here is a group of frames that we're going to sample, and also some conditioning frames as well. So that is what G is denoting here. And this part isn't super important. What's basically happening is discretization. So some of these distributions will return continuous values. So for example, what the first index of our sampled frame, uniform distribution may return 2.5 or 2.7, which really doesn't make sense. Indices need to be integers. So the high level idea is they're just making sure all of the values are integers. So what we've essentially done is we've created some group. We've created some row, which basically tells us what frames to sample and what frames to condition on. But there's a little bit more to this algorithm. So once we've constructed this group, let's say that set X already has some indices in it, and set Y also has some indices in it. If we add this group to these sets, and it results in their cardinality being larger than the threshold that we set, we essentially return these vectors. So what that basically means is once these are returned, this goes to the diffusion process. These set of frames need to be generated. These set of frames are what it'll be conditioned on, and this is what's passed to the diffusion model. If this is not the case, and we are still trying to generate frames and trying to generate a full row here, that's where we go into these last two steps here, where essentially if you haven't seen this group before, we're going to generate those frames. So if the frames haven't been generated yet, we need to generate them. If they have been generated before, then we're going to use them for conditioning as well. So the high level idea behind this is that we're randomly, there's a little bit of logic, but we're essentially randomly constructing frames to generate on and frames to condition on. So we build X and Y in this manner, and this only has to do with how we're building the sampling scheme. This has nothing to do with the diffusion part. All we're doing is building this X and Y sets, and finally the last step is when we return these sets, and that's where the diffusion comes into play, using this X and Y set, as Shane had mentioned before.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
So there's one quick thing I just wanted to mention, because this was a big question I had been reading the paper, was why do they choose these distributions, these specific distributions in that algorithm? Why wouldn't they choose some simpler distributions to use for those multiple variables? So there's a process here that they show where they kind of try and simplify the process. There's another ablation in the paper where they completely randomly choose all of those variables. And the idea is that they just lead to worse quantitative results. So if you want to look at more detail, you can reference the paper. But what this does is it just lends merit to the idea that constructing the variables in the deliberate way that they did seemed to have led to the best results. So like I had mentioned before, all of this is during training. We train the diffusion model using this completely random sampling scheme. And the idea behind that is at test time, there are all different types of sampling schemes we can use. And depending on the data set, different sampling schemes will give you different results. So if we can train our model to work on any sampling scheme, obviously it would lend more flexibility to this diffusion model, and it can work with multiple data sets or multiple sampling schemes. So what I had talked about before with the methodology, like I mentioned, was in the training section. Now, when we're talking about test time, the authors use a various number of test time sampling schemes to see how their model does. We won't go into a lot of detail on how they work. Again, you can reference the paper for that. But here's what we just wanted to show some visualizations of them. So we've seen a smaller version of autoregression, but this is kind of just a bigger figure for it. You have long range as well, where you can see that even as we're generating frames throughout the video, the start of the video is always used for conditioning. So there's some long range dependence even with the farther away frames. The authors also introduced some other test time sampling schemes where they use hierarchies, where you generate a frame at the very first row and continue to condition on that. There are some more difficult versions of it like hierarchy 3. And lastly, there are some adaptive and optimized test time samples that you can use. Again, we won't spend too much time on this, but if you have any questions, you can reference the paper for those. So now we kind of have an idea of how the training of flexible diffusion works and how the test time sampling schemes work as well. So we'll see these applications and some of the results in these next sections.
So, hello everyone. Let's talk a little bit about the data set. So the data set was generated using the Carla driving simulator. And the cool thing about it is that it provides the model interpretable measurements for temporal coherence. These interpretable measurements are speeds that are generated every second of video time, and this data is semantically meaningful to the sample routes. The output from this helps show that the video is truly continuous, coherent, and not broken down over the sampled time frame. So let's talk a little bit more about the interpretable measurements. So on the bottom right, we can see a pictograph of the training ground, stoplights, the red dots that the vehicle stops at, and the density mapping for how often the vehicle traveled there. This data set comparison works by building a histogram, which we can see on the bottom left, from the taken speed intervals and computing a cost to match the generated speed distribution with the provided distribution. This gives us a measure of how continuous and realistic the sample data is. And from this, we can make sure the sampled video is temporally coherent and photorealistic as it should be. So we can move on to the results.
All right, so now just to cover some quantitative results from the paper, they mainly use Frechette video distance, which is essentially just a video extension of the Frechette inception distance that we've seen for images, and just sort of measures how close these videos are to the input ground truth images. This GQ and mazes data set actually creates mazes, and it gives an accuracy of rooms explored. And then the Carla dataset has those metrics with the speed and whatnot that Mitchell had just talked about. But what the important thing we see here is that they're training one model here, but they end up using different sampling schemes at inference time. And on each data set, different sampling schemes seem to work better, with the exception of autoregressive, which as we showed was the essential previous work. But when we use these sampling schemes, they'll perform better in different regards. But as we've talked about, this is very data set dependent. We can see the same here with these optimized sampling schemes. I think they showed them on a separate figure because it required some additional computation, so maybe it wasn't a fair comparison. And we see the hierarchy 2 optimized beats out on GQ and mazes, and the optimized autoregressive wins out on the mine RL. And then neither of these actually outperform one of the previous unoptimized regimes on the Carla dataset. But again, just reinforcing this idea of they're very dataset dependent. So the training on the randomized scheme works best. And then here they talk about some frame level quality quantitative results, just to sort of compare to previous works where they'll do it. All these are image level, so they just take individual frames and try to match them with different distance metrics. And we see that throughout all these sampling schemes, it doesn't really affect the image quality, which intuitively makes sense. They sort of just affect how the frames are generated, like what frames are generated, but they're going to be still, I guess, similar in quality. And the CWVAE beats out in SSIM and PSNR, but the authors state that this is because these are more blurry, but these metrics favor blurry images that are closer to the ground truth. Not too sure this, but yeah, they just showed that this showed these image level metrics. And then going back to that map that Mitchell showed about the data set, their training data covers this entire town. So you can think of this as an aerial view of an actual town with these red lights being stoplights. So in the training, we have the vehicle exploring this entire environment. However, when we use the autoregressive sampling scheme, it sort of gets stuck here because there's no long range dependencies. The model just looks at the previous couple frames and just starts driving in a circle. Doesn't really explore much. Then we use the hierarchy 2 sampling scheme. If the car starts here, for example, when it gets here, it still has that long range dependency of knowing that it was outside of this loop. So it ends up actually exploring this environment, which I found sort of interesting that this is not like a reinforcement learning agent trying to explore the environment. It's just generating frames. But because of the way they've sampled, it actually ends up exploring the environment, which is pretty neat. And just here's some visualizations. I don't really show too much, but the paper published these results here. The red border means it's the ground truth video. Theirs takes a while to start. Our reproduction starts a little bit earlier, but the quality isn't great. It just shows that it can generate a town. You see the buildings moving. There's coherency between them. We also tried unconditional generation where we didn't give it any conditioning frames. And again, we just see realistic, not in the image quality, but in the sense that the trees are tracked, the yellow lines on the road stay consistent. They're pretty evenly spaced out. Just kind of wanted to showcase this site. If we have extra time, we can look at it. They have a lot of examples there, just showing different generations. So that's all we have. Do you guys have any questions?